This is exercise 1.5 second sum. So you've been given three different non-homogeneous linear equations. So we have to find the solutions for these set of equations for all possible values of lambda. Okay. So 1.5 exercise, the second and third sum are very important 10 mark questions. So let's get started. So the first thing we will be doing is writing these three set of equations in the matrix form, right? So when we write it in the matrix form, it's 1, 1, 1, 2, 1 minus 2, lambda, 1 and 4, right? This when we multiply it with x, y and z, we get the resultant as 2, 2, 2, right? So we call this A x equal to B. So to find the consistency when we are going to use the rank method, the main thing that we have to write is we have to write the augmented matrix. Hope you know by now what an augmented matrix is. If not, let me repeat. It's nothing but writing matrix A and B together. In simple terms, that's what it means, right? So if I write matrix A first, 2, 1 minus 2, lambda 1, 4, and then I'll write the matrix B in this column, 2, 2, 2. So this is how your augmented matrix will look like. Now we are going to make this augmented matrix, right, into the echelon form. So always in echelon form, the first row, first element should be 1. It is 1. So we'll try to make the second row, first element here as 0. If I have to make this a 0, what should I do? I'll say R2 is equal to R2 minus 2 times R1, right? So this will become, let me write the first row as it is. Then I'll say R2 is equal to R2 minus 2 times R1. So this becomes 2 minus 2, 0, 1 minus 2, minus 1, minus 2 into minus 2, not into minus 2, minus 2, minus 2, it's minus 4, and 2 minus 4 is minus 2. Next is, if I want to make this element here a 0, I should say R3 is equal to R3 minus lambda times R1. So when I multiply R1 with lambda and subtract it from R3, I'll get this as 0, right? So this becomes 0, then 1 minus 1 into lambda. So I'll just write it as 1 minus lambda. 4 minus 1 into lambda. So it becomes 4 minus lambda. And 2 minus 2 times lambda, right? So it becomes 2 minus 2 lambda. Okay? So till now it's fine. Next, we want to make this element here 0, right? In echelon form. Typically that's how we do it. So I'll just put a small rough work here. So to make this element here 0, I'll just write down R2 now has minus 1 and R3 has 1 minus lambda. So if I have to make this element here a 0, typically I should first multiply. So I can do R3 plus R2 to get rid of this 1. So my R2 will become minus 1 and R3 will become 1 minus lambda minus 1. This gets cancelled, eventually get minus lambda. Now R2 will be minus 1 and R3 will become minus lambda. Now how do we get rid of this minus lambda here? We say R3 minus lambda times R2. This is nothing but R3 is already minus lambda. Here you have minus 1. So multiply it with lambda, you get minus lambda. So minus into minus, it becomes plus lambda, and you get 0 here. So this is what we would be doing it in 2 different steps. So let's continue. So the first step, let's write R1 and R2 as it is. 0 minus 1 minus 4 minus 2. And as I said, in the first step we'll be doing R3 equal to R3 plus R2. So we are going to get rid of lambda in 2 steps, right? So the first step, when we do, this becomes anyway 0. This, when I add with this, it becomes minus lambda. Then you look at this, it is 4 minus lambda minus 4, right? Likewise, just like this, 4 and minus 4 will get cancelled. You'll be left with minus lambda. And here it will become 2 minus 2 lambda minus 2. So 2 and minus 2 will get cancelled. You'll be left with minus 2 lambda, right? Now the next step, what we said is we'll write R1 and R2 as it is first. Now we are going to get rid of this minus lambda here. How? We're going to say R3 is equal to R3 minus lambda times R2. So this is nothing but 0 minus 0 minus lambda plus lambda. So you get 0 here again. Here in this case it will be minus lambda plus 4 times lambda. So minus lambda plus 4 lambda is, you get 3 lambda. And minus 2 lambda plus 2 lambda, you get a 0 here, right? So your row 3 becomes 0, 0, 3 lambda and 0. Now we'll talk about some different cases. I think you can't do anything beyond this, right? So let's look into the different cases. So I'll say case 1, right? What could be the possible values of lambda? So the first case, if lambda equal to 0. So how will your matrix look? Right? 1, 1, 1, 2, 0, minus 1, minus 4, minus 2, 0, 0, 0, 0. Here the rank of A, B is equal to 2. That is, you have 2 non-zero rows. And this is also equal to your rank of A alone, right? The A matrix alone, that will also have the rank as 2, right? But you know that it is not equal to the number of unknowns. So in this case, you can say that the system is consistent because the rank is the same, right? So the system is consistent and it has infinitely many solutions because the rank is not equal to the number of unknowns. So you have infinitely many solutions, infinite number of solutions. So this is case 1, right? Now let's have case 2, when lambda is not equal to 0. Okay, how will your matrix look like? So is this clear? I'll repeat it again later. So let's proceed with case 2. In case 2, if my lambda was not equal to 0, how will my matrix look like? It will be 1, 1, 1, 2, 0, minus 1, minus 4, minus 2, 0, 0. If my lambda was not 0 and it just took the value of 1, for example, this is just an example. It will take some value, arbitrary value, I am assuming, and this will be like this. In this case, what will be my rank of A and B? My rank of A and B, number of non-zero rows will be 3. My rank of A will also be equal to 3, and therefore the system will be, and this will be equal to the number of unknowns, right? X, Y and Z. So in this case, what can I say? The system is consistent, right? Because the rank is same and since the rank is equal to the number of unknowns, we can say that the we will say that the system will have a unique solution. Okay, so for lambda equal to 0, you saw the system was consistent and many solutions, right? Infinitely many solutions. And for lambda equal to not equal to 0, you saw that the system was consistent and it had a unique solution, right? This is clear. I'll just recap what we have done. So the question was, this is a very important 10 marks, so that's why I'm doing it a little slowly. So you had to find the different possible solutions for the different values of lambda for these three linear non-homogeneous equations. So the third equation did not have an x coordinate, it had lambda, right? So we wrote this in the matrix form, then we wrote the augmented matrix, and after we wrote the augmented matrix, we tried to bring it to the echelon form. Row 2 we could easily make it as a 0. For this lambda here, we try to make this a 0, and then to remove this element here, 1 minus lambda, to make that 0, we followed a two-step approach. So first we added it with R3 to get rid of the 1, so we only got minus lambda here, and then we subtracted it with lambda times R2 to make this a 0. So in the process we got a 3 lambda here. So we took two cases where lambda equal to 0. When lambda became 0, 3 lambda also became 0. Therefore the rank of A and B and the rank of A was equal, and it was 2. That is, there were only 2 non-zero rows, but it was lesser than the number of unknowns. Number of unknowns is 3. Therefore we said that the system is consistent because the rank is the same, but since it was lesser than the number of unknowns, we said it had many solutions, infinitely many solutions, right? Second case was, we assumed that lambda is not equal to 0. So I just wrote down how the matrix could possibly look like. So instead of lambda equal to 0 here, we assume lambda equal to 1. So in that case 3 lambda became 3. This is just an assumption. So in that case the rank of A and B and rank of A was equal to 3. There were 3 non-zero rows. Since the rank was same, it was consistent, and we also saw that the rank was equal to the number of unknowns. Therefore we said the system is consistent and has a unique solution. So I think you can leave this over here, and you just give these reasonings correctly. I'm sure you will get your full 10 marks.